you, Charlie, and thank you, everybody, for the chance to speak to you this afternoon. So I'm going to talk mostly about some work done by Rodrigo Silva Lopez, a recent PhD graduate from Stanford, who's funded in significant part by a peer project in recent years. And so I want to talk to you specifically about this, how we were using some of these new machine learning technologies to support infrastructure risk analysis and risk management. But before I dig into that, I was just reflecting a little bit this week and about the session broadly and about why do we want to use these types of tools in earthquake engineering. And I remembered there was a very interesting paper in Science a few years ago from Greg Baroza, one of my colleagues at Geophysics, and some co-authors. It focused on geophysical applications, but I think a lot of it translates over to more engineering-focused applications as well. And they kind of categorize things as down these rows. So I'll kind of briefly talk this through. So one thing we can do is automation. And here I think like image classification and recognition of features and imagery is a one to think about there, where there's some sort of features we're trying to identify, and a well-trained computer can do this at a scale that we couldn't imagine as humans. So that's, I think, a natural application area. Then there's kind of modeling areas, so we all do a lot of modeling. One can be a forward simulation problem where you've got a very expensive set of calculations. You run it a few times, and then you train a neural network or some sort of other model to repeat the calculations that model is producing, but much faster. And that's the type of work that I'll be showing today, these surrogate models. There were several great talks today of others using surrogate models for similar purposes. You can do the same thing with inversion, where you're trying to invert some sort of model. I think analogy might be a site characterization based on surface wave measurements or something like that, where you're trying to infer something about the nature of the earth or the nature of a building based on outputs. You could train some sort of a machine learning model to do those types of inversions for you faster than maybe a kind of purely physics-driven inversion would work. And then the final category, the bottom row, was discovery. So there, the thinking is to try to extract features out of data in a way where we haven't previously labeled the data or haven't told the algorithm what we're looking for, but through clustering and other types of techniques, you could extract features. There, I think, it comes to mind maybe structural health monitoring applications or things like that, where we just kind of feed in data and we try to let the algorithms find structure that we maybe can't kind of pre-specify. So I think for me that helps me to think about like why, and it sometimes helps with my over-exuberant students that want to use machine learning for lots of different applications to say, what is it where this tool is solving some problem that we couldn't solve via other means. So if that strikes anybody as a useful way to structure their thinking, I hope that's helpful. And, with all of these, we've got some sort of input data. We have some sort of kind of algorithm in the middle that's going to do these types of calculations, and then some sort of output that we're desiring from them. And so if you can kind of specify your columns and specify what row you're in, that might lead to appropriate choice of algorithms. Okay, but shifting a little more specifically to our project objective, what we were thinking about is a kind of an infrastructure risk management problem. And just to dig into it and give us some sort of pseudo-realistic data to work with, we thought about kind of transportation systems and thinking about disruption to these networks from earthquake events. And so just to think about a kind of an expensive problem that we might think about, we were working with this Bay Area transportation model. It's shown in the map on the left. There's kind of tens of thousands of road segments that users can travel over. We've got origins and destinations in the model that users want to travel through, and they've got kind of travel times over each of those links. And then the model has the state-owned bridges in the region, about 2,000 bridges that are, we got some very nice help from Caltrans over the years to get some sort of characterization of these bridges, and those are potentially damageable in an earthquake event. We've got fragility functions to represent that. And if those bridges are damaged, that's going to influence the travel times on the links, and we're interested in kind of the overall impact to the users of the network. We don't have any single earthquake scenario that we know is going to happen in the future. So the seismic hazard is represented by these 1,992 earthquake scenarios. These are coming from this source model that the USGS uses to produce the national seismic hazard maps. So these are all rupture locations, magnitudes, and resulting ground motions as predicted by empirical ground motion models. And so we want to say over all of these unknown but plausible future earthquake events, what's the risk to this network of users having extra travel time or lost trips, and how might that be managed by retrofitting of the bridges? And the goal is not necessarily to get those numbers right, but to explore kind of algorithms for studying problems like that, which I think are general to a lot of our infrastructure risk problems. And when we do these analyses, at least in this workflow, we kind of start with that earthquake scenario and the ground motions. The ground motions are overlaid with the bridges, and then we sample damage or sample a damage state for each of those bridges. Then with the damaged network, we do traffic assignment. So users take trips trying to minimize our travel time. We get congestion, we get extra congestion if some of the roads are closed or limited. And then we get some sort of metric out the back. In this case, it's kind of an average travel time increase for the users of the networks taking a trip. But any metric is doable here. And with our workflow, I forget which animation's in here. The seismic, the ground motions are pretty fast. We're using empirical ground motion models. It could be done with simulations that are slower. The bridge damage is fast. It's just fragility functions. Right? That could be slow with detailed modeling. But this trip assignment is pretty slow. So there's all these trips that have to be assigned and routing that has to be done and things like that. And so the idea was, with regard to those surrogate models, is let's replace our trip assignment algorithms, which are kind of iterative algorithms and shortest path calculations. Let's replace that with a neural network. And it's going to take the inputs being the damage states of all 1,700 bridges in the network, and the output is going to be this travel time metric. And we'll just train it off of a big set of simulations, and then we'll have this fast neural network to work with instead. Yep, so that can be done by anybody with kind of good training in these neural network algorithms. There's some choices to be made. There's some that are a little bit unique to us that not just a really good undergrad with a computer science background could do. I'll highlight briefly the sampling protocols. So the first rounds of these neural networks worked very well on average for predicting the travel time. So this is kind of a scatter plot of predicted travel time increases from the traffic model on the x-axis. So that's the real explicit model that's a little slower. And then the y-axis is the same prediction from the neural network. There's a little bit of scatter here, but it's 100,000 data points, so you're just seeing the envelope. It's actually a quite good R-squared. But the model wasn't doing quite as well for the really extreme events when there's a lot of damage to the network. Most of the samples were not too much damage, and the model was doing well, but that's not really what we're so interested in if we're doing all this kind of network level analysis. So what we ended up doing, I'll just say that the model wasn't working so well at the kind of right end. Had some bias, had some scatter. What we ended up doing is kind of forcing to have extra samples from what we called the extreme events, where there was predicted to be larger travel time increases, and we could figure that out without running the traffic model. And what this plot is showing in blue is the R-squared value for the extreme events in the test data. And then the x-axis is what fraction of the training data is extreme events, these kind of large disruptive events. So as we put more and more extreme events in the test data, it did better and better at predicting those, the vertical line climbing up. The gray line is the R-squared for the overall set of data, including the smaller events, and it didn't really suffer as we oversampled these extreme events. And so it turned out if we could put in more and more extreme events in the training data, we could get a more effective model for these tail cases that we were interested in without really any sacrifice. So we just had to be a little thoughtful about how to train the model, and we could get even better performance than a more naive calibration. Once we had a calibrated model, we could use that neural network through all of those 2,000 earthquake events and simulate kind of cumulative distribution functions or exceedance probability curves for those of you in the insurance space. So these are plots. The x-axis is like a traffic loss metric, so heading to the right is a more disrupted network. And then the y-axis is the annual rate of exceedance, looking over all these possible earthquake events that could be occurring. The solid lines are what we computed when we used the explicit traffic model, and the dashed lines were from the neural network. So you could effectively reproduce these exceedance probability curves. The nice thing now, though, is so we had to generate a bunch of traffic simulations to train the model, but then we could use that trained model in a lot of different circumstances. So the baseline case is in orange. In blue, we retrofit 500 of the bridges by changing their fragility functions. And the neural network doesn't really care what the retrofit status is. It just needs to know the damage states. So those damage probabilities go down with retrofits, and the model can perfectly reproduce a new exceedance probability curve. So it's very easy to explore mitigation strategies with this neural network that's very fast. And after the training is done, so the training is not trivial, that takes a little bit of time. But to produce one of these curves with the traffic model takes 8 hours over all the simulations. With the neural network, it's basically instant. So there's like 4 orders of magnitude speed up or something like that, skipping that slow step out of the process. So that was helpful for some other things we were doing. One of the things that's a little uncomfortable with these machine learning models is the black box nature of them, right? So we just have all these bridges as input damage states that passes through this neural network, and there's some number that comes out. There's more and more focus on these explainable AI algorithms. We looked at this a little bit with this LIME algorithm, which is a kind of a popular algorithm to look at the importance of the inputs. The idea here is that if we've got some sort of output from this neural network and some sort of input variable, this variable 1 on the x-axis, you can kind of vary that input variable and see what the neural network is predicting as outputs. It's nonlinear in general. It's a very high-dimensional model. But you can imagine kind of fitting a local regression here that says, as I'm changing this input variable a bit, how much is my answer changing on the output? So this is a metric you can get out, and as that slope of that local regression is higher, that means that variable is more important. But this is in like 2,000 dimensional space, so this local metric depends on the damage states of all the other bridges and things, and so it's a little hard to extract, in our case, what does that mean for a particular bridge's importance? So what we did is we kind of extended that basic algorithm over, sorry, this is Rodrigo's animations, I don't know what's in here, animation-wise. So we take all these simulations of these 2,000 earthquakes. For each of those simulations and all the bridge damage states, we compute that local LIME coefficient, and then we weight that coefficient by how often that scenario occurs. So this gives us kind of a weighted importance over all these possible future earthquakes of how important that bridge was to the network's performance in each of those earthquakes. And so that gives us out a single metric per bridge that was relatively stable over kind of sampling schemes and things like that. And so that's a number that's kind of interesting in terms of kind of risk management actions, and just saying that this bridge's damage state is really influencing the performance of the network in a way that accounts for interactions with all of the other nearby bridges and traffic rerouting and all sorts of complexities in the real model that the neural network doesn't know about, but we're kind of extracting out with this algorithm. And so we kind of played some games with the network where we were retrofitting bridges. And so here is a plot of the x-axis is the traffic performance loss, so kind of a high number is bad. That means you're getting kind of more impacts to users. And then the x-axis is how many bridges were retrofit out of the network. So as you retrofit more bridges, these numbers come down. The bridges that we picked to retrofit, the top line is retrofitting based on vulnerability, so just which ones were damaged most frequently. So that helps, but you may be retrofitting bridges that are not in kind of central places in the network. We had a traffic importance metric of just how much traffic those bridges were carrying and trying to retrofit the high volume bridges. That works much better. And then this LIME TI metric of the bridge importance, which is trying to link the damage state with these travel times, that works even better. And so it suggests that's an informative metric in terms of system risk. However, we can do even more than that. Because we have this neural network that's very fast, you could just optimize explicitly and say, let's search for the bridge retrofits that maximize the benefit via some metric like this. And so here's an extra line here. So we used genetic algorithms to search around for combinations of bridges to retrofit. And you can do this direct optimization that works even better, as you might expect, because you're directly searching for what can do the best in terms of dropping this line. That wouldn't be possible if you were just running this traffic assignment. We'd have to do so many function evaluations, we could never kind of search the whole design space. But with a neural network that's so much faster, that's not a problem. We also looked with this LIME TI metric of does it make intuitive sense, kind of what bridges are getting selected? And we thought there was some kind of rhyme and reason to it, so that was reassuring as well. But I'll go past that. So kind of messaging around this, and in particular what's related to this AI theme from the session, I think these neural networks I left kind of convinced that it's a pretty practical tool for looking at these large infrastructure systems. So we were looking, again, at transportation systems, but anything where you have a lot of components that are mapping through to some sort of system level performance, these types of machine learning tools make sense, right? This is the surrogate modeling, kind of middle slice out of that opening slide. And these algorithms are very good at reproducing data that you give it, if you give it enough data of the right type. Speaking of the right type, in this particular case, and I think broadly with our seismic risk problems, thinking about the extreme events and making sure that the model is performing under the conditions that are of most interest to us, that's pretty important, but that's addressable. These explainable AI algorithms, they seem to be developing pretty rapidly, but they show some promise for getting more than just like a black box prediction without any sort of further insights. And then finally, we use that model, I flashed it very quickly, as a surrogate model in optimization, having this really fast function, having a function that's kind of well behaved in terms of being smooth. That really helps if you're trying to optimize a complex system, and so we found good utility there as well. Finally, I'll just note at the very bottom of the page, there's a recent paper that covers a lot of the content I covered here. The paper and other related code and resources are also available at that website down at the bottom of the slide, so be very pleased if you take advantage of any of our work or code that we've tried to share from this. With that, I'll close. Thanks very much for your attention.